In this video, we are going to discuss about generalized power function. The generalized power function is written in the form of x raised to the power of n, where x is defined to be any real number that is larger than 0, whereas n represents any real number. Sometimes people confuse between the power function and exponential function. Generalized exponential function has a form of the base a, which is a constant, raised to the power of x, where x is a variable. For power function, it is in the form of the variable x raised to n power of n, where n is a constant that represents the power which the x is raised to. In the case of a generalized exponential function, the base a has to be a real number that is positive, and x could be any real number. In the case of a generalized power function, the x has to be a real number that is positive with the power n to be any real number. So try not to confuse between power function and exponential function. The generalized power function is defined in terms of the exponential function in the following form. We're going to derive x power n in terms of the power function e power x. To begin the definition, let us look at how x can be expressed in the form of exponential function. X is expressed as the exponential function of ln of x. This is what we have learned in the previous discussion when we talk about the inverse equation for exponential of x and L of x. Then what we do next is to raise to the power of a real number n on both sides of this equation. According to one of the rules that we have seen earlier on, x is raised to the power of a and then raised to the power of b. This is the same as e raised to the power of a times b. You can think of the ln x to be a and the n to be just b. So with this, we can write down the right hand side to be just e raised to the product of ln x times n, which is just written as n times the log of x. This is how the generalized exponential function is defined. Once we have defined the generalized exponential function, we can try to take the log of the generalized exponential function. The log or the natural log of the generalized exponential function is just e raised to the power of n ln x. This is just the definition of the generalized exponential function. And since we already learned in the previous lecture, ln of e raised to the power of anything will be just equals to that anything. You can write the right hand side to be the product of n multiplied with ln x. In other words, we have just proven that based on the definition of the generalized power function, the log of x raised to the power of n is just equals to the product of n times ln x. We have actually seen similar relationship when we study the natural log. That is the power rule in the natural log. Namely, if you have a variable x raised to a power of r and you take the log, then you have this very simple rule. So can you tell the difference between this version of the power rule and this version of the power rule that applies to the generalized power function? The difference is that in our definition of n refers to any real number, whereas here r is only referred to an rational number. The real number contains also irrational number, whereas the R for this case only includes number that is rational. In other words, this version of the generalized power function is more general than this version. Both equations look exactly alike. Therefore, when you define the generalized power function, irrespective of the power, whether the power be an rational number or irrational number, the natural log of x raised to any number is just given by the product of that power multiplied the log of the x. Next, we would like to ask a question: what is the derivative of the generalized power function? We would derive the derivative of the generalized power function based on its definition, e to the power of n times ln x. We will let u to be n times ln x, so that d dx of e n ln x could be written as d dx of e power u. So we will then apply the chain rule that will give us d du, eu, and du dx. d du of eu just gives us eu, whereas du dx could be calculated from here. Du dx is then equals to n times d dx of ln x, which is 1 over x. So I write down du dx to be n over x. E power u is nothing but just our x of power n. And here we have n multiplied with x raised to the power of minus 1. So we have n raised to the power of n of n minus 1. That says d dx of x power n is simply equals to n times x raised to the power of n minus 1, where we arrive at the x power n minus 1, assume that x power n multiplied with x power minus 1 is given by x of n minus 1. We have to actually prove this before we can assume that the statement is true. So let's see how you can evaluate x power n times x power minus n. X power n by definition is e raised to the power of n ln x, whereas x power minus n, according to the definition, is equals to e power minus 1 times ln x. Then we apply the law that e a multiplied with e power b to be just e raised to the power of a plus b. That gives us e power n ln x minus ln x, which is just e of n minus 1 ln x. Then you recognize that e raised to the power of n minus 1 times ln x is then just the x power of n minus 1. Therefore, we have just proven that x power n multiplied with x power minus 1 is simply equals to x power of n minus 1. Therefore, we have just proven that the d dx of x raised to the power of n is equals to n times x raised to the power of 1, x raised to the power of n minus 1, where n is any real number. So this formula may seem very simple, and you may thought that this has been studied before. Indeed, we have seen the same result before in Theorem 4 in chapter 3.6. However, the formula that we have encountered in chapter 3.6 only applies to n equals to p over q, which says here the ratio of n over q is simply an fractional number, or simply a number that is not irrational. However, the result that we have proven here applies to any values of n, including n that is non-fractional. So in this sense, the result that has been proven here, the derivative for the generalized exponential function, is a more general version than the theorem 4 in topic 3.6. So up to this point, we have been able to show that the derivative of the generalized power function is simply equals to this. The next thing we want to discuss is to generalize the differentiation of the generalized power function to a function of u of x, which is raised to the power of n. So we ask the same questions. If you replace the x power n by u of x raised to the power of n, what do you get? So in this sense, we are promoting the single variable of x into a function of x, which is represented by u of x. Then you can apply the chain rule to answer these questions. So we will let y equals to u power n. Then we ask the question of what is dy dx. That is the same as asking what is the d dx of u raised to the power of n. And in order to answer that questions, I will resort to the chain rule to write dy dx in terms of dy du and du dx. So here you can derive dy du. It is simply equals to n times u n minus 1. The derivative of u power n with respect to x, which is just the same as dy dx, is then simply equals to n u raised to the power of n minus 1 times du dx. So here n times u to the power of n minus 1 is just dy du. So up to this point, we have just proven that d dx of u power n is just simply given by these statements here. In the very special case where you set u of x to x itself, that is, you take the function of u to be just equals to the x itself, then it is possible to reduce this to d dx of x power n equals to n times x raised to the power of n minus 1, and du dx is simply equals to 1 when you replace u by x. This is just the original version of the d dx of the generalized power function. So now the conclusion is simply that the derivative of a function of x raised to the power of n is simply equals to n times u power n minus 1 du dx. We will look at two examples on the derivative of the generalized power function. We are asked to calculate the dx of x raised to the power of square root of 2. Here, the generalized power function is in the form where the power n is taking an irrational number of square root of 2. So this is simply equals to, according to the formula we have just derived. The answer is simply square root of 2 x raised to the power of square root of 2 minus 1. So this result seems to be very trivial by applying this formula. What you have to be realized is that previously, before we have introduced the generalized power function, we only take the derivative of x raised to an fractional number, and the fractional number cannot represent an irrational number. So the fact that you can apply this rule to an power in x that is irrational is made possible only due to the definitions of the generalized power function based on the exponential function and the logarithmic function. So that explains the importance of the exponential function and the logarithmic function. It allows you to generalize the differential rule to a index or the power which is irrational. The next example we want to discuss is calculate the derivative of 2 plus sine of 3x raised to the power of I. To do this simple differentiation, you simply define a function of u which represent 2 plus sine 3x so that these questions can be written in the form of dx of u raised to the power of n, where n is representing the irrational number I. Therefore, you can calculate the derivative by using the chain rule, n u to the power of n minus 1 du dx. So here we have n equals to pi, and you have u which is 2 plus sine of 3x raised to the power of pi minus 1, and then you have to slot in du dx. Here du dx is simply equals to 3 times cos of 3x. So you slot in the expression of du dx, 3 cos 3x. That is the result of your calculation. That finished up the discussion on the generalized power function, which is the last part in the topic of 7.3, the exponential function.